bit of that already last class, so we'll continue. So newtons divided difference. Okay. So last time we were aiming at an iterative kind of a method to generate interpolating polynomials such that the first one interpolates 1 point, P0, and then the second one, P1, interpolates 2 points, making use of what you had in the previous step. And then the third polynomial, P3, interpolates 3 points, and using the P1 you get in the previous step, right? So remember we did that? Okay, so I will put up those 3 steps we had. So for n equals to 0, you get a polynomial of degree 0, which interpolates the first point, so it's just a constant, right? This we had last time. So when n equals to 1, we have a first polynomial P1 based on P0. You would take P0 and you add 1 term, it'll be A1 x minus x0. So one more time we did this, so we include 1 more point. So in order to interpolate 3 points, now we use the P1 of x plus an A2 of x minus x0, x minus x1. Okay, and okay, I should have written here. So how is this A1 computed? Well, it's computed so you interpolate 1 more point. So this is y1 minus y0 over x1 minus x0, right? We derived it last time. So, and then we also derived how to compute the A2, which would be the y2 here minus the P1 at x2 over the denominator is x2 minus x0, x2 minus x1. So that's where we stopped last time. Okay, so you know, the whole point is to find these A's, A1, A2, because they go back in. Once you plug in this A1, you would know your P1. So the whole point here is to find some kind of an algorithm in the end that would allow me to generate as many A's as I like, as I add more points to it, right? So before we continue and go to n equals to 3, let's stop and take a look at A1, and in particular we take a look at A2 and see is there some pattern that I can use to design a general algorithm. Okay, so that's what we would do. So I see that in order to compute A2, I need to evaluate P1 at x2, right? So let's take a look at that first. Okay, so some details. All right, so let's take a look. Take a look. P1 evaluated at x2. What is that? So let's see. P1 equals to that, and where A1 equals to this, and I'm going to put x equals to x2. So this would be P0, which is a constant, so it's just y0, right? Plus A1, A1 is this number, so it's y1 minus y0, x1 minus x0 times x minus x0. So I'm putting x2 here, so it's x2 minus x0. Is that okay? It's just manipulating it algebraically. Yeah?
Is the P0 of x always y0?
Yeah, that's the constant. It's a polynomial of degree 0. It's a constant.
I thought if x was x2, then it would be y2. Does that make sense?
No, it's always equal to y0, no matter what you put in.
Okay.
It's a constant, right? Yeah. Okay. Okay, so now I play a little trick. This term here, I'm going to write it as following. I take x2, I subtract x1 from it, and after I subtract x1, I give it back. So I didn't do anything, right? Okay, so I continue. So do we agree this equal to that? So I group the first two and the last two. Okay. So the point of doing this is that once I distribute this, the multiplication, then the denominator here would cancel the denominator there, or the numerator, sorry. Okay, so let me write out. So now I will have y0 plus, and I do this times the first term, so y1 minus y0 over x1 minus x0 times x2 minus x1, that's the first term, okay? Plus, and then I do this term times that, where the denominator cancels that one. Is it clear? So I have y1 minus y0. Okay, so the whole point is now I have a cancellation. This one cancels that. So okay, I can take one more step. So what do I have? I will have a y1 plus y1 minus y0 over x1 minus x0, x2 minus x1. I just write it down. So in a clean way. We okay? Now we can plug this back in and compute my A2. This is to motivate the algorithm. Okay, so A2 will be y2 minus this guy we worked out here and divided by that denominator. So this becomes y2 minus this thing, so is y1 negative y1 y0 x1 x0 times x2 minus x1 over x2 minus x0 x2 minus x1. So I copied A2 over and I plugged in the expression for P1 at x2. Is that okay? It's just manipulation. I want to write it in another way that tells me actually what's going on. Okay, so what I do now will be, I will divide the numerator and the denominator by this factor, x2 minus x1. So this will be divided by x2 minus x1, and this will be divided by x2 minus x1. They are distinct, so this is a non-zero value, right? I can do that. Okay, so then what do I get? Let's write it. So I will have y2 minus y1. This is the numerator, is divided by x2 minus x1, right? Minus, so this term times that divided by that, so that's gone. I get y1 minus y0 over x1 minus x0. Okay, and the denominator, I got rid of one factor, so I get only x2 minus x0. Is it okay? This is algebra. But you need to know what form you want to arrive. You want to write it in this specific form. So let's look at it. What do we have here? So what is the meaning of this term, for example? So this term is the term by the first two data points, right? x0, y0, x1, y1. If I compute this expression, what do I get? A1. A1. Yeah, okay. So pretend x and y, they are points on the graph of a function. What will that value be? Slope of the secant line, which is some kind of an approximation to some derivative. Do we agree? It's some kind of a f prime approximate value, maybe at x0, between x0 and x1, right? So what about this value here? Isn't it similar? It will be some kind of a derivative of that function at some point between x2 and x1. And you can think it's an approximation to the first derivative at x2, right? So you have kind of f prime at x2 minus f prime at x0 divided by x2 minus x0. What is approximately this value saying? if you look at the difference between the derivative divided by the distance, this becomes an approximation to some second derivative. Do we see? And this is A2. So you see, A1 is some kind of an approximation to first derivative. And A2 is some kind of approximation to second derivative, but written in this kind of a finite difference form, right? That's why we call this name divided difference, okay? Okay, so this, we think, is some kind of a second derivative if f is the function that you are interpolating. Okay. Okay, so with this observation in hand, so we are thinking, okay, if I do one more layer, if I go and find A3, it will be some approximation to the third derivative, and so on and so forth. Okay, so hopefully I have convinced you that fact, and now we go to the general step. Okay, so general expression for a k. So, okay, so we're familiar with the setting, so we need to say something. So assume now I have a polynomial pk minus 1. It interpolates the data of xi, yi, I from 0 to k minus 1. And then we seek a pk which interpolates one more point. Okay, that will be exactly xk, yk. And we will use the pk minus 1. Okay, so in this particular form, in this iterative form, so pk of x will equal to pk minus 1 of x plus, I add an additional term, this will be the ak of x minus x0, x minus x1, x minus xk minus 1, right? So you see from our previous discussion why it is so nice to take this form, because what you're adding here, this term, is 0 at x0, x1, and all the way to xk minus 1. So this form already guarantees that the interpolation property for pk minus 1 is preserved for pk, right? So you just need to worry about the last term that you add. Okay, is it clear? Okay, so we will use that to find exactly my ak. So use pk at xk equals to yk to find ak. Okay, so you just plug into this equation and you compute. So the ak takes the following value. So you put into xk and this shall equal to yk. So I move this over. I will get yk minus pk minus 1 xk. That's the numerator. And divided by this product, right? So x minus x0, x minus x1, all the way to x minus xk minus 1. Oh no, at k. It's evaluated at k, xk. Is it clear? Any question? Is it okay? Okay, so once you have obtained all these A's, then you can write out the Newton's form. So let's write this out. So Newton's form using all these A's, these are kind of a divided difference. So your polynomial Pn, which interpolates n plus 1 point, would take the following form. So you can write it like this. You can start from P0, which is my, which I should introduce a name. I would call this guy just A0. So I have all these coefficients as A's, okay? So this will take, the first one is A0, that's my P0. Then I add the additional term needed to make it P1, right? So this will be A1 of x minus x0. Now this is P1, right? So from here, how do I get P2? Well, I add another term. Is that right? So I take A2, and then I multiply this by one more term. Is it clear, the pattern? And then I keep going. I keep adding A3, A4, all the way to AN. Okay? So you keep adding many until you reach the last one. That will be AN. This is x minus x0, x minus x1, dot, 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 all the way to x minus xn minus 1. Okay, and that will be your polynomial, provided you have all these AIs computed. Okay? Okay, so theoretically it's clear what these AIs shall be, but we want to design some algorithm that will allow us to compute this in the most efficient way. So this is what we will cover right now. Okay, so we'll have an algorithm to compute all these. These are called divided differences. Okay, how do we compute? So these are computed in a kind of a iterative way. So you have your data set, xi, yi, I from 0, 1 to n, and you want to interpolate it. Okay, so we generate all these divided differences. So level 1, that's the first level. So we pretend these are data points of some function f, okay, which we don't know. So this is a notation. So I say f, which contains only of one of such xi that I send in, this exactly equal to yi. So I from 0, 1 to n. So I initiate the iteration by just assigning all the y's to my f. Okay, and then I do the next level. I will be using whatever you obtained in the previous level. So let's give a specific index. Let's say fx0, x1. So I have 2 of these x in this fancy bracket. Okay, so how is this computed? Well, this was computed as following: f at x1 minus f at x0 over x1 minus x0. So it uses what you have previously. Okay, subtract the 2. These are always neighboring index. Okay, they're always neighbor of each other. So you evaluate at x1 and then evaluate at x0 and subtract with that. So say now if you want to compute x1, x2, what would you do? This will be f at x2 minus f at x1 over x2 minus x1. Is it clear what you do at this level? Then you can go through all of them and you will have n of such things, right? Here you have n minus 1. But since this is generated by comparing each neighboring pair, you get 1 less. You get n of such things, right? And then you continue. Then if I include 3 neighboring index, So how is it computed? Well, it's very much similar to what I did over here. So I will use what I have in step 2. I will have f. So the first number here will be take away the first index and just copy the rest. Okay? So x1, x2 minus, and then you take away the last x and you copy, all right? So x0, x1, okay, f. And then you are divided by the biggest index x minus the smallest index x, okay? x2 minus x0. Is that clear? Let's do one more just to make it clear. So what if I have x1, x2, x3? So I will have f. So I take away the first number. I'll get x2, x3 minus f. And then I take away the last one. I'll get x1, x2. So what should I divide it with? x3 minus x1. Is that clear? I'll give you the general expression. Wait a second. Yeah, okay, so now take a look at how we computed A2. Don't we see that this guy here is f x1, x2? And this guy here is f x0, x1, right? And this guy here is f x0, x1, x2. Do we see that? Now you see what I am aiming at, right? Okay, so this procedure can be carried on to n. So I'm erasing this A2 here. So the general one, let's see, you can continue doing this all the way to the nth level. You will have this f at x0, x1, xn minus 1, xn. How would that one be computed? Well, I would take away the first number, and then I start from x1 and go all the way to xn. This difference minus f, and then I take away the last one. Okay, so I have x0 to xn minus 1. So these two shall be computed already at step n minus 1. Now I'm using it. Is that clear? So the denominator would be the last xn minus the first x0. Okay? And if you have computed all that, then you get the following. I didn't prove it, but I have. So A0 will be f at x0. A1 will be f x0, x1. A2 will be f x0, x1, x2. And you see the pattern. And an will be f x0, xn. And these will exactly be those coefficients in the Newton's form of the interpolating polynomial. Is that clear? It's a bit heavy. Okay, so we kind of approved for this one, and for this one, and for this one, right? I just motivated this expression. I didn't really show you rigorously that an exactly takes that form for any n. Okay, so a detailed proof is in the lecture notes. If you are curious, you can go and read it. So all it does is just an induction step. So assuming the expression holds at level k, and then show that it holds at level k plus 1. Okay, if you are curious, you can read through it. It's nothing hard, but just lengthy, right? So, which I will not go through in class. Okay. So what we will be doing now will be having actually an algorithm. after understanding how these AIs are computed, we want an algorithm that we can eventually code. This will be a homework problem. Okay, so make sure you understand the algorithm. So computation of all these divided differences in the algorithm. Okay, so we are thinking as a computer scientist. I understand what I have to do. Now, how do I design it? As an algorithm. Okay, so what we'll be doing here, okay, so we'll set up a table. So first column are putting the x values. So x0, x1, x, I need a bit space, x1, x2, and should I take an x3? Maybe. And the last one is xn. Okay, so these are the x values, so they don't really get much tangled with the rest. Okay, now I compute all these divided difference. So the first one will be taking 1x in the bracket. So by definition, what will I fill in here in this column? It will be all the y's, is that right? We'll start from there. So this will be y0, y1, y2, y3, and yn. So that's the first column. Okay, and then let's do the next one. So let's say we want to compute f of x0, x1. What do I need? Well, I know from my definition this will be this minus that divided by this minus that. And then this column will have one less element than the previous one. And it keeps getting less and less and less, right? So in the end, you just need actually a triangular shape to store your data. So it's your choice. You can choose to make it an upper triangle like this and leave all those down there 0. Or you could do a lower triangle, store all data here and leave the upper one 0. Either way would work fine. Is it clear? So I would choose to use a lower triangle here. Is that okay? Okay, so it doesn't really matter, whichever. So that means I will not compute this one. I will compute this one, which will use these two values. So this will be the f, x0, x1. That will be computed as y1 minus y0 over x1 minus x0. Is that clear? And I can continue and fill this column. Do you see I can do that? So f at x1, x2 will be y2 minus y1, x2 minus x1. Is that right? I can keep doing it until the last one. So f xn minus 1, xn, what will it be? Yn minus 1, and then over xn minus 1. Is that okay? So you generated the second column, and then you can go on, keep going on. So this will have 3 of these x sending in, right? So and then I don't need to compute this guy if I follow my lower triangle structure. So this will be the first non-zero one, which I'll be using these two information to get that one. So that will be the f of x0, x1, x2, which will be this minus that, f of x1, x2, minus f of x0, x1 over x2 minus x0. Is that right? And I can keep doing it until I fill the last place. So this will be the f of xn minus 2, xn minus 1, xn. Okay? So you see this can be continued. You can keep doing this n times until at the n minus 1 time, you end up with only 2. And then you do it one more time, and you get only 1. And then you cannot perform this anymore. And then you stop. Is it clear? So blah, blah, blah. You can do many, many times until the last step. You keep using these neighboring 2 to get 1. So until the last step, you get just 1 here. So this is f of x0, x1, all the way to xn. And this is computed by using f at x1 to xn minus f x0 to xn minus 1 over xn minus x0. Then you stop. Okay. So you have a triangular shape of data, but you know you only need to find those coefficients, A0, A1, and A2. So what information in this triangular data? So you could generate a matrix to store that, and then just keep this upper half 0 and don't touch it, right? So what elements are important that I need to, what informations are important that I need to take out in this matrix?
Just the diagonal.
Only the diagonal. Do we see that? That's A0. Is that right? And this is A1, we see? And this is A2. So let me mess up. So this is A0, and this is A1, and this is A2, and all the way down, and this guy here is AN. And then you take all these out, extract them from your matrix, and then you form your polynomial like that. Is that clear? Is the procedure clear? You're supposed to code it for the next homework. So how would you code it? Think about that. How would you code it? Do I need a for loop? Do I need one for loop or need 2? Is one loop enough?
2.
I need 2 because I need to fill a matrix, isn't it? I could have a loop in I for the column, so I go from 1 to n, right? And then for each I need to do another loop, right? Let's say k will be from I to n, right? So the first one will be from 1 to n, and the second will be from 2 to n, the third will be from 3 to n. And then I will have to fill in these numbers. Is that right? So two for loops shall be good enough. And once you finished it, and then you have this matrix, and you go along the diagonal and take them all out and store them in the vector A. Is that clear? Can we handle that? It's not too bad, right? Okay. Okay, so what I plan to do next, well, just slow down a bit. I just throw this heavy algorithm at you. So we'll take an example to make sure these information gets settled, all right? So take a little example. Okay, so we want to write Newton's form for the following data. So it's always that secret cosine function that I'm using. So 0, 1, 1, 0, 2/3, 0.5. I add another point, 1/3, 0.866. Okay, so that's the data. I have 4 points, so I need a polynomial of degree 3. Okay, that will interpolate this data. And I want to do it the Newton's form, so you must be able to do this. Okay, so there are not many questions I could come up to test you in the exam that you can finish in 10 minutes of time. And this is a very good candidate. Show me you know the procedure how to generate these A's for the Newton's form. Okay, so let's set up this table as we did there. So just follow it. It's nothing very fancy. So xi, what will I have? 0, 1 2/3, 1/3, right? So let's set this up. Okay, so putting the yi, so 1, 0, 0.5, 0.866. Okay, so what about the next one? F of xi, xi minus 1. You don't need to specify, actually. So I don't need to compute this guy. I'll start from here. I need to fill in 3 numbers. So how do I get this number? 0 minus 1 over 1 minus 0. Is that clear? So let me just write it. 0 minus 1 over 1 minus 0, which is -1, right? And then how do I fill in this number? 0.5 minus 0 over 2/3 minus 1. Is that clear? So 0.5 minus 0 and 2/3 minus 1. So you get 0.5 up there, you get -1/3 down, so which gives you -3/2, so 1.5. Okay? And then the last one will be 0.866 minus 0.5 over 1/3 minus 2/3. Is that clear? Okay, so you got -1/3 in the bottom, and then if you work this out, is -1.098. Okay, let's don't take too many decimal places. All right, so I need to go on. I need a bit more space. Okay, so for the next one, I don't need to fill in here. I don't need to fill in here. I need to fill in 2 numbers. So what will be that number? This number minus that number on the numerator, that's clear, right? So -1.5 minus -1 on the numerator. What will be in the denominator? It will be this x minus that one, right? Remember? Remember? It will be x2 minus x0, not the neighboring x, okay? So that will be 2/3 minus 0. Okay, so once you figure out what you have to do, well, I'll just give the number. That's -0.75. Okay, so this one will be -1.098 minus -1.5, the 2 neighboring one, divided by, what will be the denominator? It will be this one minus 1. Is that clear? Because that's f of xi plus 1, xi plus 2. So you need to skip 1 x, right? The last one minus the first. So 1/3 minus 1, and that gives me -0.603. It's okay. So I see now I need to do only one more step, because nothing to be done here, nothing to be done here, nothing to be done here. I just need to figure out one number. So the numerator is always just this subtraction. What's on the denominator? Which x minus which x?
1/3 minus 0.
Yes. So you have to take the last one minus the first one. Is it all clear for everyone? Is it clear? Okay. So commonly people make mistake with the denominator. The numerator is quite obvious. Okay. So it's the last one minus the first. All right. So that gives me about 0.441. Okay. Stop there. And now, what are the important numbers? Let's circle them. That's important. The diagonals. That's important. That's important. And that's important. Is that right? So let's take them and form this polynomial. Okay, so you have to show me you know. So A0 will be 1. A1 will be -1. A2 -0.75, and A3 is 0.441. Question?
And at the bottom right corner, should that be 1/3 minus? I don't understand why it's minus 0 or minus.
Because it has to skip 2.
Oh, you skip 2. You don't
Yeah.
just go to the top one.
No,
Okay.
because what would this be? This would be the f of x0, x1, x2, x3. So the denominator will be x3 minus x0,
Okay.
right? Yeah.
Okay.
So you skip the 2 middle x's to get it. Yeah. Okay, so can we form this polynomial? What will it be? A0, which is 1, plus A1 is -1 times x minus x0, which is 0. Is that right? Plus A2, -7.5 times x minus x0, x minus x1, which is 1, right? And then the last one, 0.441, x minus 0, x minus 1. There's one more point, the next x, which is 2/3. And that's your polynomial. So is the algorithm clear what one has to do? Any questions on it? Now let's take a look at this algorithm. So remember, we first talked about Lagrange form, and then we criticize it, and then we say we come up with something that works better. What was that about the Lagrange form that we criticize? That it's not
Flexible.
not flexible with respect to adding additional points, right? If you add a point, you have to do everything all over again. So this algorithm, does it actually overcome that difficulty? Do we see that it's more flexible? Let's check the flexibility. Now, say I want to add a point, add another point. Let's say, let me just go over and kind of a silly and mess this up. Say I want to add additional point, 0.51. This is the one I want to add on. I see, I ran another test, I get that data with me. Do I need to throw away what I have done? So what do I have to do? I just need to add one row down here, isn't it? I just put in 0.5 and 1. I keep all that computation. I have to work out all these numbers down here, and then I will have an additional number down here. That will be my A4. Is that clear? So it is flexible, right? So it is flexible. Okay. Yeah. Okay, so next time we will start with